Hello everyone. In this video, we're going to begin our discussion of conditional statements. So let's take a look at the notes and see what the learning objectives are for our first video on conditional statements. We're going to talk about what a Boolean is, specifically how a Boolean is used in an expression that evaluates a true or false, and that's what a Boolean condition is. Then we'll talk about relational and logical operators and how they can be used in order to construct Boolean conditions. Then we'll talk about something called short circuit evaluation, which is what your compiler does in order to save time and execute your code more optimally. And then we'll talk about De Morgan's laws, which are really handy laws that you can use in order to complement and simplify a Boolean condition. So for the warm-up task, go ahead and open up your VM and code up an empty main function in a file called booleanfun.cpp. We'll use booleanfun.cpp to code up some booleans and print out their values so we can see how Boolean conditions are evaluated. So let's begin by taking some notes. A Boolean is either true or false. You can think about a Boolean like a light switch that can either be in an on state or an off state, or you can think about it like a bit in terms of binary. A bit can be 0 or 1. You can also think about it as closed or open. So Boolean is really just one of two states, either true or false. So a Boolean expression, or more commonly known as a Boolean condition, is an expression that evaluates to true or false. So in C++, there's a data type called bool, which we've seen a little bit before, and it can be used to store true or false, a Boolean. So let's say we have a variable called is sunny outside. And since it's summer right now when I'm recording this video, I'm going to set this to be true. So you can already see in this one variable expression or variable declaration and initialization that bool and true are reserved words because they're showing up in this bold font face. Bool is a data type and true is a reserved word. We also have false. So I could come down here and later set is sunny to false. Now, true and false are reserved words we can use in order to assign a value to a bool, but we can also use integers. In C++, 0 is false. And anything other than 0 is true, which is kind of interesting. For example, 10 is true, 100 is true, -2 is true, 1 is true. As long as it's not 0, then it's considered to be true. Typically, the value 1 is reserved for meaning true. So let's write that down. But don't be fooled. Anything other than 0 is true. Typically, you'll see 1 used for true, but it doesn't have to be 1. So let's take a look at this. Integer 0 or 1 in action. If we print out is sunny, when is sunny is true, and then let's print out is sunny again after we set it to false, and we'll see what's printed. 1 and 0. So 1 is used when sunny is true, and 0 is used when sunny is false. So something to definitely keep in mind is though we use true and false for convenience in our code, we can also use 0 and 1. And in fact, when we print out Booleans, we'll see their integer representation. Now let's move on to a little bit more advanced use cases of bool beyond just assigning true and false or 1 and 0. Typically, you'll use Boolean conditions with relational operators. So here are relational operators: less than, greater than, less than or equal to, greater than or equal to, and not equal to. And I want to just take a little moment and comment on the equality operator. Recall that when we were first learning about variables, we would have something like this, and I really emphasize that this is the assignment operator, not the equality operator. So when you read this, you don't want to say int x equals 5. Do not say that, because it's not true. X does not equal 5. X takes on the value of 5. X is a location in memory, and it can store a value. The value that it's storing is 5, because 5 is assigned to x. Now, we could construct a Boolean condition, since we know about the relational operators now, and we know what a Boolean is. We could have something like bool, I'll just call it y, is assigned x equal 5. So the double equal sign is one operator, which is the equality operator. And this does test if something is equal to something else. Left operand equal to right operand. And this will evaluate true or false, which we could then store using logical assignment into a bool variable. This one happens to be called y. So in summary, how I would recommend training your brain to read this variable declaration and assignment would be bool y is assigned x equal 5. And then equal in your mind is how you're going to essentially represent the equality operator versus the assignment operator. I've got some examples here that I want to work through to show you how these relational operators work in action. So let's say we've got the following integer variables. X is assigned 3, y is assigned 4, max is assigned 100, and min is assigned 0. And then we have a char, ch, which is assigned lowercase c. So I've got a few little Boolean expressions down here. And remember, Boolean expression evaluates to true or false. So let's go through each one of these and figure out if they evaluate to true or false. X less than or equal to 0. X is 3. 3 less than or equal to 0. 3 is not less than or equal to 0. So that will evaluate to false. X equal y. Does 3 equal 4? It does not. That is false. Max greater than or equal to min. 100 greater than or equal to 0. That is true. Ch less than lowercase a. Okay, so is lowercase c less than lowercase a? So this is a little tricky, but remember that characters are really storing integers representing ASCII codes. So if we quickly pull up an ASCII table, we'll see that lowercase a is integer 97 and lowercase c is integer 99. So this is really asking, is 99, which is lowercase c, less than 97? And it is not. False. Max. Is 100 true or false? Since it is not 0, 100 is actually true. Min not equal to 0. 0 not equal to 0, that is false. 0 does equal 0. Now we've got some arithmetic operators here. We've got a plus and a minus. So let's do the first one. Arithmetic operators have higher precedence than the relational operators. Here shortly we will see the operator precedence table again, just for review, so we can see how all of these new operators fit in. But I will tell you that arithmetic operators have higher precedence than relational operators. So we'll do 99 plus 1 first, which is 100. Then we evaluate, does 100 equal max? Max is 100. 100 equal 100. That is true. And then the last one, we'll do the subtraction first. 0 is min, 0 minus 50 is negative 50. Is negative 50 less than 0? It is, that's true. Now, a good exercise that I'd like you to do now is pause the video and type these variable declarations and initializations and these Boolean expressions up in our booleanfun.cpp file and confirm that we have evaluated these correctly. So for each one of these expressions, you can print it out and it'll tell you 0 for false, 1 for true. So go ahead and pause the video and do that now. All right, we're going to move on now to logical operators. There are 3 logical operators, and I'm going to write these on the whiteboard so that we can derive that truth table. So let's start with logical and. Logical and is 2 ampersands in C++. That's the operator. Now there's also a single ampersand operator, so it'll be a very tricky logic error to track down if you intend for a logical and, but you only put 1 ampersand. So be very careful and take a mental note now. Logical and is 2 ampersands together to make 1 operator. So logical and evaluates to true when both operands are true. We'll see a few examples of this here shortly. Next is logical or, which is a double pipe. So if you look on your keyboard, it's usually right above the enter key, which is where your backslash is. So shift backslash will usually give you that pipe character. 2 pipe characters. Make a mental note, just like you have for your double ampersand for logical and. So the operator logical or is true when at least 1 operand is true. And then our last one is logical not, which is a single exclamation mark. And what logical not does is flips true to false and false to true. Logical and logical or are binary operators. They have 2 operands. Logical not is a unary operator. It only has 1 operand. So in order to show several examples and provide very definitive cases for and or and not, we typically construct a truth table. If you've taken a philosophy class before, you have likely seen truth tables before. If not, then this will be first exposure to truth tables, but you'll likely see them again at some point in the future as you take perhaps a philosophy or a discrete math class. So typically for a truth table, you have variables. We'll have 2 variables, P and Q, since we have binary operators that can have two operands, and you iterate through, or you list out all possible combinations of true and false for your variables. For example, P could be false. I'll use 0 for false. And Q could be false. P could be false, while Q could be true. P could be true, while Q could be false. And both P and Q could be true. Now we'll go through and, or, and not for P and Q so you can see how these evaluate. Let's start with not. Let's add a column for not P. So we'll go through each row of our table and we'll evaluate not P for that row. So when P is false, not P will be true because it flips true to false and false to true, flipping false to true. So not P when P is 0 is 1. Not P when P is 1 true is 0 for false. Now let's add a column for logical and. So we'll evaluate P and Q. Recall logical and is true when both operands are true, false otherwise. So when P is false and Q is false, false and false is false. False and true is false. True and false is false. True and true, both operands are true. So P and Q is true. Now let's do P or Q. Recall, logical OR returns true when at least one of the operands is true. False or false, false. False or true, at least one operand is true. This is true. True or false, true. True or true, true. So with our truth table now, we have a definition for how our logical operators, not, and or, evaluate for all possible cases of the operand's values. So I've got a few examples here that we can use to apply logical operators. Let's say that we have the following variables. Temp is assigned 50, max temp is assigned 90, percip is assigned 2.0, num votes is assigned 20, votes needed is assigned 20, and elected is assigned 0. So let's evaluate these. Recall order of operations. We'll do parentheses first. So we'll evaluate, is temp less than max temp? Is 50 less than 90? That is true. So the left operand of logical and is true. Percip greater than 0, 2.0 greater than 0, that is true. True and true, and we can even refer back to our table. True and true is true. So this whole expression evaluates to true. Our next one, same thing, we'll do parentheses first. Num votes greater than or equal to votes needed. So 20 greater than or equal to 20, that is true. Or not elected. Elected is 0, not 0, not false is true. We have true or true, which is true, because at least one of our operands is true. In fact, both of them are true. So same thing here. Give you a task. Code up the above examples to check our work. Go ahead and pause the video and work on that in booleanfun.cpp. Now, one thing that I'd like to point out on our last example here, since by definition, logical OR is true when at least one operand is true, since we knew that the left operand was true before we needed to evaluate the right operand, we actually didn't need to evaluate the right operand. True or anything is true. And this is called short circuit evaluation. Your compiler does this. In the case of logical OR, as soon as one of the operands is known to be true, the other operand is not evaluated because regardless of what it evaluates to, this whole expression will be true. We also have an equivalent short circuit evaluation for logical AND. Why don't you take a moment and think about the case where the right operand doesn't need to be evaluated if we know something about the left operand of logical AND. Since logical AND is only true when both operands are true, as soon as one operand is known to be false, the entire logical AND expression will evaluate to false. So your compiler, when it's building your executable to be run on your machine, will insert code such that whenever the left operand or one of the operands is known to be false of a logical AND, the other one does not need to be evaluated. The whole expression will be false. And I have that summarized here in this section on short circuit evaluation. So let's take a moment and review our operator precedents. Since we've learned quite a few new operators, we know about relational operators and logical operators now. So from highest to lowest, I've listed out here the operators that we know about so far. And then here's kind of a more holistic table that includes more operators, including the ones that we're going to learn soon. So highest precedence would be calling a function, which we're going to talk about in much more detail later. And then we have our unary operators, including, check this one out, logical NOT. So logical NOT has very, very, very high precedence. And then we have our arithmetic operators, and then we have our relational operators, noting that inequality operators like less than and greater than are at a slightly higher precedence than our equality operators, which are at a higher precedence than logical AND, which are at a higher precedence than logical OR, which are all at a higher precedence than assignment. So here you can see a table bringing in more operators, like for example, we've got our typecast over here and our parentheses up here, which have the highest order of precedence. All right, so let's take a look at an example applying the operator precedence table. Let's say we have x plus y is less than z minus a. How will it evaluate? Which operators have the higher precedence in this expression? So we've got plus and minus, which are here, and then we've got less than, that is here. So we'll do the arithmetic operators first, from left to right, and then we'll do the inequality operator. So this will evaluate x plus y first, then z minus a, and then the inequality operator last. Here's another example here, which I encourage you to pause the video now and work through. The answer to how this expression is evaluated when these variables take on these values is in this picture here. The last thing we have to talk about theory-wise is complementing conditions. The logical NOT operator is also called the complement operator, and we can use it in order to complement expressions. So, for example, let's say we have a Boolean expression Temp is greater than 32, where temp is a variable that stores perhaps the temperature outside. So temp greater than 32. Complemented would be applying the not operator to the entire expression, as you can see here. Now, when we negate a greater than expression, the greater than becomes less than or equal to. And this makes sense if we say it out loud. If I said not temp greater than 32, then that would mean temp is less than or equal to 32 if temperature is not greater than 32. And we can see that written here. Same with if we have temp equal to 32. If we negate this expression, we have not temp equal to 32, which means temp is not equal to 32. Now, these rules make pretty good sense when we're talking about relational operators, because if we say it out loud, it makes sense in terms of our English grammar, our English language. But for logical and logical or, it might be a little bit trickier. Thankfully, we have De Morgan's laws, which we can use to complement compound logical expressions. So those would be logical expressions that include logical operators like and or. So let's go ahead and take a look at De Morgan's laws. De Morgan's laws state that the complement of x and y, where x is the entire left operand of logical and y is the entire right operand of logical and, noting that these themselves might also be compound logical expressions or expressions that have relational operators, Boolean expressions of some sort. This is equivalent to not x or not y. So an easy way to remember this is think about distributing the not to each operator and the operand. So not x becomes not x, not y becomes not y, and in negating the operands x and y, you also have to flip logical and to logical or. Truth table-based proof of this is included at the bottom of the notes for this lesson. We also have a similar De Morgan's law for logical or. If we negate a logical or expression, then we get the negation of each operand, logical and it, together. So these are really helpful when complementing expressions, but also when we get to learn about if statements, and we have the idea of something called an else. And the else only executes when the Boolean condition associated with the if statement evaluates to false. So that would be when it's not true. And you can see where not true may come into play working with De Morgan's laws. So I have an example here at the very bottom of the notes. Let's say we have temp greater than 32 and skies equal to S or skies equal to P, and you wanted to complement this entire expression, which would be like putting an exclamation mark and parentheses around the whole expression. Then you would essentially negate the left operand of logical and, which is this entire expression, temp greater than 32. If temp is not greater than 32, then it's less than or equal to 32. The and becomes an or, and then we negate the entire right operand of logical and, which is this whole expression in parentheses. And now we've kind of got a new subproblem. It's kind of like we have a negation here for negating the right operand of logical and now we can think about applying De Morgan's law again, but this one for negating a logical or. So skies not equal to S is the negation of skies equal to S. Flip the or to and. Sky is not equal to P is the negation of not sky is equal to P. One way that you could prove to yourself that this expression is in fact equivalent to the complement of this expression would be to construct a truth table like I've done here and compare that the columns actually end up being the same when you take the negation compared to what you get with De Morgan's law. So that would be a great task to go ahead and do right now as we conclude this video. The last thing I'll say is learning all about these logical operators, relational operators, De Morgan's law, short circuit evaluation, etc. is laying the groundwork for learning about conditionals, which starts with an if statement. If something is true, if some Boolean condition evaluates to true, then execute this code. So you get conditional execution. All of our code so far has been sequential, where we start at the top and we execute line by line. Now with conditional, we'll still start at the top, but when we hit something called a branch, like an if statement, we'll only execute some code if that condition is true. Then we'll continue on sequentially. So that kind of wraps up the first two types of statements that algorithms are composed of, which would be sequential statements and conditional statements. The third one would be iterative statements, which would be repeating a set of code while some Boolean condition is true. And we will cover iterative statements soon. So you can definitely see the importance of Boolean conditions in terms of conditional and in terms of iterative statements. And those three types of statements that algorithms are composed of are listed here. So in the next video, we're going to learn about if statements, which will allow us to execute some code if some Boolean condition is true.